Hello there. In this video, we're going to look at the thinning property of Poisson point processes. It's also related to something called Raikov's theorem. And we're going to do this with an example involving a multi-class or a two-class queuing network that is otherwise an MM3 network. So let's begin by importing the Ciw Python package, and we'll define our network. So queue and create network. Define our arrival distributions. So we'll say arrivals, and here we're going to use a dictionary because we need to specify the distributions for each class. So let's say, for the sake of argument, that we have an adult class and a child class, where, let's say, q.dists exponential. Let's say a rate of, and actually this is where I want to show the effect of splitting it. So let's say that we have like a base input rate, just to be explicit, and let's say that that's 5, and we'll say proportion adult is equal to, let's say for the sake of argument, 0.4. And similarly, we'll have proportion child be 1 minus the adult proportion. And where we're going to show this kind of Raikov or theorem or rate thinning theorem is to say, well, it should be, Raikov's theorem is basically an additive decomposition of the rate into subgroups, and if the total rate can be split by this proportion, then we just need to multiply the proportions. Or there's also a less direct route of arguing this using the thinning property of Poisson processes. So proportion adult, that will multiply into that, and I guess it needs to know where that rate comes from. That's the base input rate. And we need to close our list here. And then for child, we'll change this up to be the child proportion, which is just the complement, right? Now let's do the service distributions. We'll just copy paste that. Service distribution. And here for the service, we're going to say it doesn't really depend on that base rate at all, or those proportions. But we will say maybe there's a rate of 7 and a rate of maybe half as much, 3.5 for child. And then we'll specify the number of servers for each node. So for this single node, there's 1. So it's a single node network, as it were, but you've got 2 different classes of customer arriving, adults and children, and the fact that we can split this up, we can split this total input rate for a total amount of incoming demand up by these proportions is a very convenient mathematical property. So let's see about actually running this as a simulation. Let's say if name is equal to dunder main in a string, then we'll set our seed of, let's say, 0. And then we'll set up our simulation class instance, our object. There's our network that we defined above. And then we'll grab records. And we'll say simulation get all records. And I forgot one of those things that you really need to do, which is to actually run the simulation. So let's simulate until maximum time of, let's say, 50 for the sake of following their example. And then for just taking a look at something, we could look at, say, records 0 to see that entry. But they also show another interesting thing here, which is maybe we want to go back and look at kind of the rough proportions of how many of each class we got. In fact, maybe let's just skip to that. So let's create a counter from collections, import counter. And then we'll call counter on our, well, let's do a less comprehension. So for record dot customer class for record in records. And let's print that. Okay, we should be good to go to see kind of this breakdown. Let's pull this into, a separate terminal, and let's run it. And so we got, the majority, one might even say, is approximately 60% versus the 89. We could have put this in our code, but let's just grab, like, say, 138 divided by 138 plus 89 should be pretty close to 60%. And there you go. It's about 60%. So the thinning property is pretty intuitive, and it might be so intuitive that you may not realize that sometimes it doesn't actually hold, that for some types of distributions, you actually can't proportionally split certain kinds of parameters this way and still get the interpretation of it changing basically the expected values or of this kind of closure of additivity. If I think about Raikov's theorem of adding the adult count for the Poisson process for adults, plus the number of children arrivals on the same interval, and that should somehow just like add to the intuitive total rate that you hope that it should, is actually not something that's just simply true. So if you're not familiar with Raikov's theorem, maybe we'll throw this in here. Raikov's theorem. I'm not going to formally state it. There's some stuff about like they need to be statistically independent and whatnot. But if I have two Poisson random variables x and y that are statistically independent, that there will be, for the Poisson distribution, assuming they're both Poisson, it'll also be the lambda for x plus the lambda for y. And that's a really nice property. And it may just not be obvious to everyone that this doesn't actually hold. And maybe we should come back and find an example of where it does not in fact hold. But Raikov's theorem supposes something like this, that x is or follows a distribution that's like a Poisson of lambda, whatever x is, and similarly that y is a Poisson. It's a very nice property because it means that if I spelled lambda wrong, but anyway, that's fine. Lambda. There we go. So Raikov's theorem, we're assuming x and y are independent, then their sum will also be Poisson distributed with these corresponding sums of lambdas. So if you thought about that there's some total lambda, is equal to the sum of those two lambdas, where we could also think about that as being a breakdown by percentages, right? Lambda total times percent or probability of x being the population. It's like a subpopulation kind of mixture sum kind of thing going on here. And also for y. So that's a very nice property, and that's basically what's going on here. Is we have this like total rate, and we're saying that some proportion of that total rate is children or adult. And so you might find this to be the most like obvious, terribly boring result, but it's actually just something that's not true for general distributions. Okay, I think we've probably beaten that one through as much as we're going to, beaten that dead horse or whatever, but it is actually a very useful property to be able to assume mathematically, and we know that under assumptions of Poisson distributions that this actually does, in fact, hold. That's the thinning property in a pinch as well. Of the thinning property is formally stated more in terms of like sum of Bernoullis, where the number of Bernoullis itself is Poisson distributed, results in a sum that is also Poisson distributed, and it all works out in a logically equivalent way, but Raikov's theorem is kind of a nice shortcut statement of it. Okay, that was more theory than anything that's like really new, because I think we've already covered in the very early tutorials in this series, you know, multi-class networks, but just so you know explicitly that for some distributions, we can talk about these kind of proportion rates. Now, I think we've also probably covered the relationship between Poisson and exponential, but if we haven't, let's just say briefly that the exponentials are the inter-arrival times, right? But if you look at an interval of time and you say, well, how many events arrived in that interval, and the inter-arrival times within that interval are exponential, that gives you a Poisson count variable with a rate that corresponds to the rate of the exponential. So they're monotonically related to each other. So anyway, that's probably enough for this video. Hopefully that helps you better understand how you might, as a modeling trick, kind of split demand by percentages in a pretty straightforward way. It's not just random guesswork. There's some mathematical theory when we're dealing with Poisson and exponentials that actually make sense of that. And with that, I wish you luck on your next simulation product. Take care.